In our previous lesson, we have introduced definite integrals. Now we're going to be discussing some properties of the definite integral. Now, if I were to start by recalling that the integral of f of x between a and b, where a and b is a subset of the domain of the function where the function is continuous. Now, if capital F of x is an antiderivative of small f of x between a and b, the definite integral would actually be capital F of b minus capital F of a. So this is how we'd evaluate the definite integral over the interval ab. In this first property, we have the lower bound and the upper bound to be equal. So the integral of f of x between a and a is in fact 0, and that is because of the definition of the definite integral. Because if f of x, the antiderivative of small f of x between a and a, by definition that's f of a minus f of a, which is 0. So whenever you have a definite integral where the lower bound and the upper bound are equal, in that case the definite integral is immediately equals to 0. Now, however, if I have the definite integral of f of x between a and b, so it would be the opposite of the definite integral of f of x between b and a, because this one would in fact be equals to capital F of b minus capital F of a, while this one, the definite integral between b and a, would be f of a minus f of b, and f of b minus f of a is equal to negative into f of a minus f of b. So this is why whenever you switch the bound of the definite integral, that integral is in fact the opposite of the one you started with. Now in this third property, we're just indicating that the definite integral of f of x between a and b is in fact a real number. However, if we look at the indefinite integral of f of x, now that would in fact be capital F of x plus k. Now the indefinite integral is a function. Now it's a function where small f of x is the derivative of capital F of x. So over here we're looking at a family of functions. For each value of k we have a different function. So antiderivatives are in fact representing family of functions. However, when we evaluate that integral over an interval between a and b, that would end up giving us a real number because of the fact that we're evaluating the antiderivative at the upper bound minus the antiderivative at the lower bound. So f of b is real and f of a is a real number. Consequently, f of b minus f of a is in fact a real number. And in this fourth property, we're indicating that if we're integrating a function defined by a constant times f of a. Now a here represents a constant. So if we're integrating a constant times f of x, in that case we would just multiply the integral of f of x by that constant. So we can, if you want, take that constant outside the integration, but that property only works when a is constant. If a is variable, we cannot in fact multiply the integral of f of x by a, the same way you'd see in this property here. And this property is also valid for indefinite integrals as well. If we're integrating here f of x times a, that would be the same as a times capital F of x plus k. Now in this fifth property, now properties 5 and 6 work if the upper bound and the lower bound are opposites. Now if we're integrating a function between negative a and a, where of course f would be continuous over this interval. Now over here, if f is an even function, in that case the integral of negative a of fx between negative a and a would be 2 times the integral of f of x between 0 and a. And if f is odd, and we're also integrating f of x between negative a and a, then that integral is immediately equals to 0. That is because of the symmetry of the function when f is even with respect to the y-axis and when f is odd with respect to the origin. However, these properties are really useful in order to quicken up the work or in order to simplify our integrals. Now, it would be easier to evaluate an antiderivative of fx perhaps between 0 and a than to evaluate it between negative a and a. And over here, one should notice that f is odd, then that integral you can immediately set it equals to 0, justifying it by saying since f is odd. So we're going to be doing a couple of examples here over these two properties. For example, if we have the integral from negative 1 to 1 of f of x, which is in fact defined, so let me just define the function by x squared minus 1. Now, if f of x is equals to x squared minus 1, then this function is even because f of negative x is negative x all squared minus 1, which is equals to x squared minus 1. So f of negative x is equals to f of x, then f is even. So since f is even, we can say that this integral is equal to 2 times the integral from 0 to 1 of x squared minus 1 dx. And we just evaluate the integral of x squared minus 1 between 0 and 1 and then multiply it by 2. Now I'm going to evaluate both sides in order to show you that you'd eventually end up with exactly the same answer. Now if I were to start with the left-hand side. Now that is 1/3 of x cubed minus x between negative 1 and 1. So that is 1/3 minus 1 minus into negative 1/3 plus 1, which is negative 2/3 minus 2/3. That is a negative 4/3. However, on the right-hand side, we do have 2 times the integral of 1/3 of x cubed minus x, but this time between 0 and 1 and multiplied by 2. So it's 2 into. At the upper bound, it's 1/3 minus 1. At the lower bound, this is 0 and this is 0 when x is equals to 0. So it's minus 0. So over here it's 2 times negative 2/3, which is equals to negative 4/3. So you notice you end up with exactly the same answer. Now it's okay if you did not notice that f is even and you could apply this property. Eventually, even if you still evaluated the integral the same way I did here on the left hand side, you would still reach the same answer. This property is just simply a shortcut whenever you notice that f is even. Now, similarly here, if f is odd, now if I were to consider the integral of, for example, x cubed dx between negative 1 and 1, and I'm going to show you that this definite integral is in fact equals to 0 because of the symmetry with respect to the origin of an odd function. Now f of x equals to x cubed. Now that is an odd function because f of negative x, that is negative x all cubed, which is negative x cubed, so that is negative f of x. So f of negative x being equals to negative f of x, in that case we can say that f is odd. So over here, if I were to integrate, now an antiderivative of x cubed is in fact 1 over 4 x to the 4, evaluated between negative 1 and 1. Now at the upper bound it is 1 over 4 minus, at the lower bound it's 1 over 4 into negative 1 to the 4. Now the exponent here is even, so negative 1 to the 4 is in fact equals to 1. So we end up with 1 over 4 minus 1 over 4, which is equals to 0. However, again, it's okay if you did not notice that f is even and you can immediately use this property. That is okay. If you evaluate the integral, you're going to eventually end up with the integral equals to 0. However, if you've noticed that f is odd and the bounds are opposites, in that case, you can immediately set the integral equals to 0 since f is even. However, just keep in mind that these properties only work when the bounds are opposites. For example, here negative 1 and 1, negative 1 and 1, they could be negative 2 and 2, etc. So this only works when the bounds are opposites. Now, if we were to move to the last set of properties, now if I consider the interval AC here, that is a subset of the domain of the function. And if we have B to be an element of that interval, so if we have here the interval AC where B is somewhere in between. So property 7 actually says that the integral from A to C of f of x is in fact equals to the integral from A to B plus the integral from B to C. So over here, if I had, for example, the integral from negative 1 to 2 of f of x dx, and we know that 0 is in that interval, so over here we can say that this integral is equals to the integral from negative 1 to 0 of f of x dx plus the integral from 0 to 2 of f of x dx. There are times where this property is useful in fact. So again, the integral from A to C is equals to the integral from A to B plus the integral from B to C. And this is in fact very useful when you're evaluating areas or volumes using definite integrals. And over here, of course, these properties are true whenever you're dealing with an integral where the lower bound is smaller than the upper bound, naturally, because over the interval AB, A should be the lower bound is smaller than the upper bound. So if A is smaller than B, if the lower bound is smaller than the upper bound, then if the function you're integrating is positive, then in that case the integral of f of x between A and B is positive. You will end up having a positive value when you evaluate this integral. Similarly, if the function is negative, in that case the integral of f of x between A and B will end up giving you a negative value, and that is of course true when the lower bound is smaller than the upper bound. Similarly, if you have f of x to be smaller than another function g of x over the interval AB, where AB has to be a subset of the domain of both functions. Of course, if A is smaller than B and over the interval AB f of x is smaller than g of x, in that case the integral of f of x is smaller than the integral of g of x between A and B. And similarly, if f of x was greater than g of x, then the integral of f of x would be greater than the integral of g of x. So I remind you that these properties are true when A and B, the lower bound is smaller than the upper bound over that specific interval. Now that is it regarding the properties of definite integrals. Now in our next lesson we're going to be tackling the substitution method using definite integrals. Now we have already tackled the substitution method with indefinite integrals. Now we're going to see how we could use the substitution method with definite integrals.